Good morning. Well, it's morning for me anyway. It might be a different time of day for you. This is chapter 13. So one comment that people made on chapter 12 was that the sound of the pen on the tablet is a bit noisy. I'm going to try and write more softly. I think it's just a feature of the pen. It's not like something I'm trying to do to be annoying. It's just the tip of the pen is a bit weird. Anyway, so I'll try and write more softly. So chapter 13, the title of the chapter is Integral Domains, but I'm going to alter it slightly. So because it's a bit more, it's integral domains and fields. Oops, that's spelled wrong. And so what these are, basically, to give a little intro, is that when we move from groups to rings, we get to more familiar structures, right? So when we went from groups to rings, things got more familiar. Right, in the sense that we pick up more operations, and so behavior is sort of a little more familiar. So let's say we get addition, therefore subtraction, and multiplication. We don't necessarily get division, so that's something to consider. And so there's still some things missing, of course, from familiar territory. So there are still familiar things missing, like division, among other things. From familiar, let's say familiar structures. So one of those things is the concept of something called a zero divisor, which is a term you may not know, but you sort of use this fact all the time. So let me bring that up because that'll be the first definition that comes in. So let's say one thing that's missing is the following. So I'll give you an example. So when you're solving an equation, say in the real numbers, suppose you got the following. Something like x plus 1, x minus 1 equals 0. We can assume one of them is 0. Right, so we then know either x plus 1 is 0 or x minus 1 is 0. So basically there's some integrity there, right? When you have a product that's 0, one of the two must be 0. But this doesn't necessarily have to be the case, right? So the assumption here is that if a, b equals 0, then a equals 0 or b equals 0. In algebra, this is sometimes called the zero product principle. That may be a term you're familiar with, but it doesn't have to always be the case. Right? So in a ring, this isn't always the case. So for example, in Z6, we have 2 times 3 is 0. But neither of those is 0. So that leads to our first definition, right? The first thing of the day, which is 2, an integral domain. So here's the definition. Let me break this down. So an integral domain is basically a ring. It's a commutative ring, and we'll look at why, in which none of these things kind of happen. So here's a precursor to that definition. So let's say if R is a commutative ring, then A in R is a zero divisor if there is a B, right? If there exists a B in R with AB equals 0. So for example, well, like the one we just saw as an example, but here's a different one. So in Z10, we see that A equals 5 is a zero divisor because 5 times 2 is 0. Whereas, for example, A equals 3 is not a zero divisor because there does not exist a B in Z10 with 3B equals 0. Now this may not be obvious, you may have to try them all, but give them all a try. You'll find out that you never get 0 if you do that. Now just a little note. So there's a reason we require commutativity. So I'll tell you why. So the reason is, in a ring, it's possible to have AB being 0, but not BA. So if you have a situation like that, then it's unclear whether you should call these things zero divisor or not, right? So in a ring, it's possible. In other words, if the ring is not commutative, it's possible to have AB being 0, but BA not being 0. So in that case, like, it becomes unclear, like, do you call these zero divisors? So in such a case, should we call them zero divisors or not? So the answer is not obvious. So let me give you an example. In M2R, right, so this is the set, this is the ring of 2x2 matrices with real entries. So if you look at the following product, 1 0 0 0 times 0 0 1 0, that is 0 0 0 0. But if you look at, say if we look at the reverse, 0 0 1 0 times 1 0 0 0. In that case, we get 0 0 1 0. So because of this, it would be hard to figure out, like, what should we call these things zero divisors or not, right? So to get rid of the ambiguity, we'll make sure the ring is commutative so this doesn't happen. So to remove ambiguity, require R to be commutative. So here are a couple of examples, a couple more examples. Actually, before, hold on, I wanted to, so actually before I do the examples, next definition. So, a commutative ring with unity. Remember, unity is like a 1. It's like something you multiply anything by and it leaves the anything alone. So a commutative ring with unity is an integral domain if it has no zero divisors. So in other words, i.e., whenever A, B is 0, we must have one of them being 0. Or both. But let's say either A equals 0 or B equals 0. So in other words, it behaves more familiarly. Right? So here are a few examples. So these are all integral domains. And so some of these may not surprise you. Some of these may not be so obvious. Z is an integral domain. ZP, when P is prime, is an integral domain. The real numbers are an integral domain. They're rational numbers. Z bracket X, this is the set of all polynomials with integer coefficients. You may need to check in your head that some of these are actually rings before we go too further. Before you go further, and also the set Z root 2. So this is the ring consisting of real numbers that have the form a plus b root 2, where a and b are integers. So again, this is totally not obvious, right? The first, I think, like let's say this guy should be pretty obvious, this guy should be pretty obvious, this guy should be pretty obvious, this guy should be pretty obvious. This one right here, maybe not so obvious, but maybe if you think about it, it's okay. This one possibly not at all obvious, right? Although you might say like, well, it's a subset of the real numbers, so that's enough. A couple different ways to look at things. But these are all integral domains. So let's look at a few examples that are not. So here are some examples. These are not. So for example, Zn, when n is not prime. So we saw an example earlier in Z6, 2 times 3 is 0, but neither of those are 0. Z plus Z. So we haven't looked at this as a ring, but you can think of it as a ring, and that you can add 2 elements just pairwise, and you can multiply them pairwise. And so this is not, because, for example, 1, 0 times 0, 1, you multiply the first 2, you get 0, you multiply the second 2, you get 0. And of course something like M2R, because it's not not even commutative, as we saw. So it couldn't even begin to talk about whether it's an integral domain or not. Right? So just a note before we move to fields is, if you notice, we required on the left-hand side, it says a commutative ring with unity is an integral domain. So the reason it has to have a unity is for historical reasons. It's possible to look at commutative rings that have no zero divisors, but don't necessarily have a unity. So, so those are not considered integral domains for historical reasons. So we require a unity for historical reasons. That's all. So the big thing then that emerges from this, actually before we look at fields, is the following theorem. So like when you have an integral domain, what do you get out of it, right? So what you get is cancellation. So in other words, this is what we get. Suppose R is an integral domain. Suppose A, B, and C are in R, with A, B equals AC and A not 0. Let me write that properly. And A not 0. Then B equals C. In other words, we can cancel non-zero things, right? Which makes sense. Like in other words, it's familiar to us. This is something that we do regularly, right? Now, little note here, in group theory, we do this because A has an inverse, but this isn't the case here. Right, so in groups, we cancel using inverses. This is not the case here. Right, so keep in mind that we cannot assume that A has an inverse. Right, like this is not built into this. Right, A is not necessarily a unit. Remember, in a ring, what it means is if it's a unit, it has an multiplicative inverses. This isn't necessarily the case. So the proof of this is a little sneakier. So we're going to assume that AB is AC. So subtract from both sides, factor out the A, and then since A is not 0, B minus C is. That's because it's an integral domain. So B must be C, QED. So we can cancel, but it's not because of multiplicative inverses. It's because of the fact that it's an integral domain. So keep that in mind, because when we go into fields right now, that's when we get multiplicative inverses. So that's not coming into play right here. So 3 fields. So now we're going to look at the case where things do have multiplicative inverses. So basic definition. So a commutative ring with unity is a field if every non-zero element is a unit. Remember, that means has a multiplicative inverse. So note that like we have to have a unity here to even talk about the multiplicative inverse. So a little note here. This is the reason why this has a unity. So we must have a unity in order to even consider units. That's why here, right? So for example, let's do a few yes and no. So the following are all fields. Everybody has a multiplicative inverse except 0, that's okay. Q. The complex numbers C. The set. This is a not obvious one. Z sub 3I. This is the set of all A plus BI such that A and B are integers. Yeah, that's the list I wanted to give. So just to clarify, this first one should be obvious, the second one should be obvious, this third one should be obvious, this fourth one is not at all obvious. All right, so you know, consider it, think about it, but don't necessarily attempt to prove it. We will talk about how later, or you can write a multiplication table down, you can see it, but don't panic overly much. And then these are not. So if you notice, what's missing from the above is the integers as a classic example. So that is not a field, right? There's no multiplicative inverse for the number 3, for example. And then things like Rx, this is polynomials with real coefficients, right? There's no inverse for x plus 1. There's no polynomial that you can multiply by x plus 1 and get 1. Right? So before we go further, there's this sort of like question, like how do fields and integral domains relate? Right, like is every field an integral domain? Is every integral domain a field, etc.? So that's the first question we'll answer here. So first, theorem. Every field is an integral domain. This means the property of being a field is stronger. So the proof of this is pretty straightforward. Suppose R is a field and A, B is 0. So I'm going to claim one of them is 0. If A equals 0, we're done. If A is not 0, we just multiply it by its multiplicative inverse. All right, just to be clear, it's multiplicative inverse. And then we get B equals 0. And that's the end. So this tells us that if you're a field, then you're an integral domain. Right? Now, the reverse is not true. Right? Let me put that as a specific point. So note, the reverse is false. So a classic example, Z is an integral domain, but not a field. If you have AB equals 0, then one of them must be 0, so it's an integral domain. But there are lots of things with no multiplicative inverse. However, the following is true, that if R is a finite integral domain, then it is a field. So Z is sort of excluded from this because it's not finite. Right? So the proof of this is actually pretty sweet and quick. Right? So this is what we'll do. We'll say let R be a finite integral domain, and let A be an R, oops, not that kind of R, be an R with A non-zero. So what I need to do is find an inverse of A. Right? Well, if A is 1, we're done. So otherwise, look at all of these. Right? So look at A to the 1, A to the 2, A to the 3, dot, dot, dot. Right? So since R is finite, 2 of these somewhere must be the same. Right? They couldn't all be different. Right? So since R is finite, we must have 2 the same. So what this means is there exists an I, let's say, greater than j with a to the I equals a to the j. So if that's the case, we can cancel, right? Because we're in integral domain, and in integral domains we can cancel. So what I'm going to do is I'm going to cancel the a to the j. Okay, so we're in an integral domain, which allows this. So we get a to the I minus j is 1. All right, so I'm canceling an a to the j from both sides. So if this is the case, then we can say that a times a to the I minus j minus 1 is 1. And now we found the inverse of a. This is the multiplicative inverse of a. And that's the end, QED. So that's the end of chapter 13. Just to summarize, right, every field, right, fields, let's say, are a subset of integral domains, which are a subset of rings. The difference being in a field, we have multiplicative inverses. In an integral domain, we have AB equals 0 implies A equals 0 or B equals 0. And so this is sort of where the focus is. Keep this structure in mind as we go forward, looking through different kinds of rings, integral domains, and fields. That's the end of 13.